Ciao! Hi everyone and welcome to this first video about a new series concerning probability and stochastic processes. And today I will introduce you to a very important theme, which is nothing but the Brownian motion. A stochastic process, Wt, for every t which is greater or equal than 0 is called Brownian motion if we basically can satisfy four different properties, which are W0 is equal to 0 almost surely, which means in a probabilistic sense that we require W0 equals 0 with probability equal to 1 or 100%. Second property, Wt trajectories must be continuous in time, which means essentially we do not have to have any discontinuity. I don't know if you are familiar with the concept about continuous functions, but I can imagine that if you are watching this video, you do. So in order to put it shortly, very shortly and very purely, in a mathematical sense, you can say that a function is continuous if you can take a pen and draw a curve on a piece of paper without removing the pen from the paper, which is basically that the function is actually continuous. So we do not have jumps or discontinuities. Third, for each p, q, r, s such that p is less than q, which is less or equal than r, which is less than s, we have that wq minus wp is independent from ws minus wr, and these two quantities are called increments of the Brownian motion, in the sense that you are taking only the y-axis difference between the 2 points corresponding to q and p in this case, and s and r in this case. The fourth property says that for each r less than s, we have that the increment related to s and r, which is ws minus wr, should be distributed like a normal variable with mean equal to 0 and variance equal to s minus r. This is a very important property and we will use it extensively in the next presentation, and I think also in the next videos. And so let's figure out what the Brownian motion looks like if we try to plot it on two Cartesian axes. So let's start by putting some axes on this slide, and let's fix, of course, the Brownian motion into the y-axis while we will set the time into the x-axis. Okay? So we have that the Brownian motion is basically a curve like this one, which is zigzagging up and down without any regularity, and this is basically obtained in this way for what concerns the increment. So let's put on the x-axis the 4 points we have just discussed about, p, q, r, s, and let's try to move on to the y-axis. So in this case we will obtain the increments as the difference between the y coordinates on the plane. So this is very trivial, but it's just to give you an idea of what the Brownian motion looks like if you try to plot it. We will investigate further, of course, how you can obtain a curve like this, and an important thing to say is that this isn't the only curve you can have about Brownian motion. So this is not the Brownian motion, but this is one possible realization of the Brownian motion, since this is the main principle which rules for what concerns stochastic processes. So you do not have a unique curve for every experiment you try to perform, but you can in general have a set of some finite curve, or in this case an infinite set of curves. This means basically that if you try to plot the Brownian motion infinite times, you will probably almost surely obtain different curves. So let's go back about the increments, which are here reported for the sake of simplicity on this graph. You can see that the double arrows stand for the increments that I have to put in this short presentation for you. So the first one is the first increment, and the second one is the second increment. Of course, you can place P, Q, R, S, and S everywhere, okay, in the x-axis. So this is a very trivial concept, so I don't think you have any problem or difficulty into sorry, I'm not very able to translate at this hour, but you will not have any problem to acknowledge this. So let's investigate further the Brownian motion, and in order to continue our investigation about this specific stochastic process, we will focus on the last two properties, so the independent increments and the normal distribution which characterize every increment. So let me point out one thing. I do not want to give you some more details and to weight this too much for what concerns the first two properties, since even if they are quite complex to demonstrate and to show, we will not have any element more to add into this context, okay? So if you want to investigate more, I can suggest you in the comments some statistical and probability books where it is explained why the two properties hold. But let's now focus on these two last properties, which are very useful, and again I repeat, we will use them extensively during our further probability and stochastic processes lessons. So let's just simplify the convention, so we can put a delta before the W in order to indicate that this quantity is an increment, and this quantity is an increment too, of course, while we can insert into the brackets the Q and P in this case, and S and R in this case, which stands for essentially that you are considering an increment with respect to Q and with respect to P in this case, where Q is greater than P, and this is the same concept for S and R. So in this case, in order to give you a more comprehensive vision about this distribution for the Brownian motion increments, I've plotted with a simple script in MATLAB two different probability distribution functions for the Brownian motion. So in the first case, I considered, for example, you can see here Q equal 2 and P equal 1, which lead us to a normal distribution with 0 mean and 1 variance. And the same reasons hold for the case Q equal 2 and P equal to 1.5. So I'm sorry if I'm not drawing perfect right lines, but I don't have a touch pen. I am only moving my mouse with my hand. But let's take this apart. I expect to acquire more professional instruments if this series will go on and further. And Well, in the second case, I was saying that we have, of course, 0 mean and 0.5 variance. So, as you can see here, we have always that our mean is equal to 0, while the variance is given by the difference between the two instants we are considering. So let's move on now into the concept of independent increments. And let's try to take the expectation in order to characterize what independent increments means. And essentially, if you take the expectation of the product of the two different increments with respect to Q and P and with respect to S and R, you can, of course, transform the expectation of the product into the product of the expectation. And this comes directly from the concept of independent random variables. And this is 0. Always, in every space and time, this is 0, since you have that the increment has always 0 mean. Okay, so this is related to this and also to this. Okay, so you have always that your mean for a certain increment is 0. So this is basically the concept of independent increments, which lead us to this big yellow arrow right here, which basically says that if we have two independent increments, we have always that their expectation with respect to the product is 0, but this is a trivial concept. Now, let's move on into an important fact about the covariance of the Brownian motion. And in order to start this sub-argument, let's now first take a look to a pure Wiener process. So, not an increment in principle, let's consider Wt as a pure value for the Brownian motion at a generic point in time t. Well, surprisingly, or maybe not so surprisingly, you can write something like this. So Wt is equal to Wt minus W0. And why is that? Well, if you remember the first property, this is equal to 0, which means that we are not adding anything to the right of this term. But in any case, this is useful if we want to convert this into an increment, because this is also an increment with respect to the Brownian motion. Sure, this is an increment with respect to the first instant in time, which is 0, but is still an increment. So again, this is an increment which is of course normally distributed with 0 mean, and in this case we have that the variance is equal to t, since the difference in time is always t in this case. Okay, so now let's move on and compute the covariance between two different let's call pure Brownian motions here. In the first case we will take Wt, and in the second case Ws, with a generic case with s minus less than t. So let's start applying the definition about the covariance between Wt and Ws, which is nothing but the expectation of the product of the two processes. This is because they have 0 expectation, 0 mean. So remember that in this case we should have always minus the expectation for the first term and minus the expectation for the second term inside square brackets. So this is between brackets, conventional brackets. I try to draw this, but I am very bad without a pen. I'm trying to move my mouse, but in this case we have mu of Wt in this case, and the same will hold for Ws, of course, but this is 0, so we will not consider it. Okay, so this is why the expectation here is given by the product only of WT and WS, and we will not consider also the mean, because this is always equal to 0. So we do not want loss of generality. So we can rearrange this very short formula by adding and subtracting the same quantity here, which is the square of the WS. And why is that? Well, because in this case, by using the linearity property of the expectation, we can transform this into two different expectations. So in the first, we have the expectation of WT times WS minus WS squared plus the expectation of WS squared. And this is a very useful trick, since you can then rewrite in the line below the first term by isolating WS. So in this case, since we have that S is less than T, we have that this is an increment with respect to T and S, and this is a pure, let's say pure Brownian motion. So this expectation is always equal to 0, since they are independent for what we saw just in the slide before. So the only term which lead us to some result here is the second term, which is the expectation of WS squared. So this is nothing but the variance of the pure WS, which is S. So in this case, we can generalize this concept by saying that the covariance between two pure Brownian motions, so between two pure Wiener process. Okay, I'm sorry if sometimes I used the term Brownian motion improperly with respect to Wiener process, but I'm sure you got it. So this is the minimum between S and T. This is a non-trivial result about the covariance, and it is useful to know this property. Go on, and let's try to look like let's try to focus on how to obtain the Brownian motion in practice, because in this case we saw that the Brownian motion in general has continuous trajectories, and we saw that the Brownian motion must be equal to 0 if t is equal to 0, and we saw the other last two properties, which are not really useful if we want to try to obtain with the MATLAB or Excel some useful results. So let's try to put this into practice. So let's start by considering a first toss of a fair coin. So, and let's call the random variable which is associated with this result as x1. Okay. So this is simply a Bernoulli variable with equal probabilities. Equal probabilities, since we have just said that the coin is fair. Okay, so you have the same probability to obtain a head, and with respect to the probability of obtaining a tail. So let us assume to associate +1 if the coin is head and -1 if the coin is tail. That is, essentially, let's put the things like this. So x1 is equal to +1 if the coin is H and -1 if the coin is T. Okay? We can repeat in general the same experiment by tossing the coin n times t time. So x1, x2, up to x and t. Okay, so all these random variables are identically distributed, and they are of course independent. So they are what we call in statistics and probability, they are IID, which stands for identically distributed and independent random variables. So I understand that the following concept can be a little bit hard to understand, but if you will watch the video about the central limit theorem and about the law of the large numbers, you will have the vision which is more clear. But in this specific video, let's now forget about this and let's take this as given. Okay, so you will have a more clear picture if you will see the video about those two things. So let's define a quantity like this, which has a subscript n and depends in general from t. And so w and t is equal to 1 over the square root of n times the sum starting from j equal to 1 up to nt of xj, which is nothing but a generic Bernoulli variable associated with the fair coin. Okay, so let's try to define something like this, and let's take this, I repeat again, as given. So we can obtain, this is a very powerful result, which says that we can obtain the Wiener process, the continuous Wiener process, as the limit for n which goes to infinity of w and t. So we are passing from the discrete realm, let's put the things like this, into the continuous realm. And this is a very powerful result, since we can in principle obtain a rough estimate about the Brownian motion also in discrete time. And this is also very nice if we can implement it for example in our computational engine like MATLAB or Excel. And for your sake of completeness, I've put here a very simple try I made about figuring out how the Wiener process can be obtained into Excel. You can of course try to refine more and to modify this script, but this is very stupid. I don't think that you will have troubles in understanding it. So in the first column of this simple script, I've just put this formula, so equal round of rand 0. This means that I am generating a random number which is 0 or 1, okay? But we have to put into -1. So in the second column you can see that I have simply converted the 0 obtained before into the -1. Okay, so this is, for example, one case, and all of these are cases about this simple reasoning. So in this case I can manage, okay, the definition that I've put here in this slide before. So in the third column, the last column, I have put all the sum of the term. I'm sorry, this curve is very bad, but okay, I try to put a new one which is less terrificant. Okay, like this and like this. Okay, so the first row here, this row, is 0, since we have to consider that the first property of the Wiener process says that W0 is equal to 0 almost surely. So in the first case we have 0. And this is why this row is highlighted in light yellow, okay? So in the third column I've performed nothing but this sum, okay? This sum here, okay? So -1 in the second row consider is nothing but 0 plus -1, and for example this 4 is equal to 3 plus 1, okay? This is nothing but the definition of this simple sum. So if we try to plot this, we can see this zigzag envelope on the right, okay? And if you try to refresh this stupid script here in Excel, you will see that the Brownian motion curve will move. For example, you can obtain something like this, or again something like this, okay? So this is in order to say that, as we saw before, we don't have the Brownian motion, we have some of the possible outcomes of the Brownian motion, so one of the possible curves. Okay, so in this case I have not considered this term, which is only a term which modify this amplitude, but will not modify the envelope, the general envelope of the curve. So it is my intention to go further into the law of large numbers and into the central limit theorem. We will see those important results in the next video. You can ask me, why did you start with the Brownian motion then? Well, this is a very good question with no answer, unfortunately, in the sense that I decided to start with the Brownian motion only because I like this specific argument. So there is nothing strange, nothing is into darkness. Okay, so let's go on into the next video with those two properties, and I hope that you enjoyed this video. So let's see us into the next episode, and I hope that you enjoyed it. Ciao.